There are other fields that we might use in this class from time to time, and they are very important for certain applications with matrices. So I'm going to introduce those now as well, even though they're not introduced in your book at the beginning, or actually anywhere, aside from the sense that the book does everything over a field and it doesn't necessarily matter which field you're working with. Okay, but what these are is these are the fields of the form FP, which is going to be, here P is a prime number, and this is the field of exactly P elements. I mean, we could take a step further if we wanted to make things more complicated and deal with fields with P to the power n elements, but let's just stick to a field with a prime number of elements. So first of all, I'm telling you that there is a field that has exactly a prime number of elements, and this is already very different than the kinds of fields we've been looking at, which all had infinitely many elements. But if we have a prime number, and this is something that tends to get proved in abstract algebra, let's start with a very tiny prime, 2. So if I have addition and multiplication, what I'm going to do is I'm going to define multiplication just like I would in the reals or the rationals or the complex numbers, but I'm going to define addition to be modulo 2, where 2 is our prime. So this is the case of P equals 2. These tables. And this turns out to meet all of the field axioms. For example, you can see right here that every single element has a multiplicative inverse aside from 0. How do I know? Well, if I have 1 and I want to get back to 1, I can just multiply it by 1. So boom, there is only one element that's not 0, so this has a multiplicative inverse. Depending on how much group theory you've done, you're probably very familiar with the group ZP, or the cyclic group of order P, or some of you might call it this, and you might use exponentiation notation as well, which is also fine. But what the difference is here is we're allowing addition and multiplication together. And we do have the distributive law, associativity, all of these things work. Of course, this is a very tiny example. Maybe let's try and do another one. Let's do, I don't know, F5. 5 is a nice prime. That's not too large for us to make a table. So if I want to do addition, 0, 1, 2, 3, 4, 0, 1, 2, 3, 4, I'm just going to get something like this. And when it comes to multiplication, well, the first row and column are going to be kind of simple here. And the next row and column are going to be kind of simple here, right? And now we have 2 times 2 is 4, 2 times 3 is 6, which is 1, and 2 times 4 happens to be 8, which is 3. And if we actually know that this is a multiplicative group, we could actually just use Sudoku rules at this point. I mean, there has to be a 4 in this row, so it has to go there, because you can't have 2 4s in the same row. But if we don't know that, that's fine. We could actually figure this out in a different way. 3 times 3 is 9, and if we're doing everything modulo 5, well, we could subtract multiples of 5 until we get to 4, or just think about it as what's the smallest non-negative number that is equivalent to 9 modulo 5, and that ends up being 4. So we get this for our multiplication table. And this ends up being the field with 5 elements. We can see what the inverses are here. The multiplicative inverse of 3 is 2, because 3 times 2 is what gives me 1. 2 is 3. 4 is 4. The multiplicative inverse of 4 is itself. And the multiplicative inverse of 1 is itself. And we don't require 0 to have a multiplicative inverse, which is good because it doesn't. And here, if we're looking at additive inverses, well, the additive inverse of 0 is 0, the additive inverse of 1 is 4, of 2 is 3, of 3 is 2, and of 4 is 1. It's the number that takes us back to 0. So this is going to play a role if we talk about coding theory. Things like sending signals, where we're allowing a certain amount of errors, but we want to make sure that we can correct up to a certain amount of errors. And I'm not going to say anything more about that now. I mean, there are many more applications than just that. But this is an important thing for us to be able to work over. And for example, if we have matrices, we can do everything that we can do with normal matrices over this field. Like, let's say we do this F over F2, and I wanted to row reduce this. Well, what would I do is I'd add a multiple of the second row to the first. What multiple? Well, 1. If I add 1 times the second row to the first row, I'd have 1, 1 plus 0, 1. And I get 1 plus 0, which is 1, and 1 plus 1, which is 0, which is why I get a 1, 0 here. So we can work over this. We can take determinants of matrices here. The determinant of this is 1. The determinant of this is 1. The determinant of this, well, if we wanted to take it, what would we do? We'd take 1 times 0 minus 1 times 1, which is minus 1, which is 1, because we're in the field with 2 elements. So we can do all of the things we've done before. We can solve systems of linear equations and play with all of the tools we've already developed. It really doesn't matter which field we're working in. So far we have the rationals, the reals, the complex numbers, and maybe the field with p elements in it that we can work with as well. And like I said, in many situations where we're trying to say certain things about matrices, we don't even need to know what the field is. Unless we're talking about a specific matrix, then we'd need to know what the field is. But if we're trying to say just a general property of matrices that they have when their entries are in a field, we don't have to think about which of the fields we're going to be dealing with. We can just prove these sorts of things in general. So that's a very, very short introduction. If you'd like some exercises, you might want to try to prove some of the field axioms for these fields f sub p. You might need a tiny bit of number theory in order to get the multiplicative inverses bit, because it actually has to do with solutions to a certain type of equation that you usually do early on in that class. But aside from that one, they're not all so difficult. Some of them might be, but some things that you can try if you like. And I guess that's it for our fields. And now we can start talking about something that's maybe not a field, but we're going to be working with it as well. And it's something that's very similar to a vector. And we'll get to that next.